Good evening. My name is Manetno Prakash. I'm here for online discussion on the from the third week lectures of water and wastewater treatment that is being taken by Bhanu Prakash sir from IIT Kanpur. I am from IIT Kanpur and I am here for my PMRF duty. So as already announced, this class schedule on every Tuesday from 7 to 9 p.m. and we meet via Google Meet using this link, and all the video are all the discussed lecture are being uploaded on this YouTube channel. So coming to the third week of the lecture, in which these five topics were discussed. The first was water quality and its water quality, that is, and quality with respect to total suspended solid and pathogen, that is TDS and pathogen. Sorry, TDS no, total dissolved solids. Total suspended solids and dissolved solid. All these contribute to water quality. Then we discussed about the wastewater treatment plant. Basic principles means how water is being treated and what are different units in the wastewater treatment plant. Then we discussed about the primary treatment, sedimentation and its basics. And finally, we discussed about sedimentation and its different kinds, that is discrete and flocculant settling. So again here I will be discussing some important questions and it related to it some concepts. Uh, so no one has joined. I will continue. The first question is related to the municipal corporation. The first question which is here, these questions are from previous year assignments and you can expect similar type of question this year also if you are appearing for your exam. So the first question is the municipal corporation must handle a daily volume of 720 meter cube of water. It is found that our flow rate is 16.5 millimeter per day. Depth is 3.5 and depth of this settling tank. I will discuss what is this settling tank on, and the width of this settling tank is 5 meter. You have to calculate the length of this settling tank in this length of the rectangular septic tank that designed for removal of discrete suspended particles. So before answering this question, one should have idea what is settling tank, what is this discrete suspended particles, how this depth, width, this overflow rate and volume. So before discussing this question, I will discuss some of the basic concepts, that is primary sedimentation tank. So just wait 1 minute. Sorry. So the coming to the first thing is that what is this primary sedimentation tank? So this is a sedimentation tank which consists of a settling zone where all the suspended particles settles and be removed these suspended particles from our system. Sorry. We remove Kavin, welcome to the lectures. I have already started. Please confirm, are you able to see my slides and am I audible to you? I hope I am audible to you and you are able to see my screen. Yes, sir. Thank you. So all I was saying that we are here for discussing some of the basic questions and concepts that has been discussed in Big Three related to water quality and wastewater treatment. Wastewater treatment. If you have gone through the lectures, some basic principles were discussed and all the different kind of units that is present in wastewater treatment. So related to it, the first question is a municipal corporation must handle a daily volume of 720 meter cube per day of water. It is found out that overflow rate in that settling tank is 16.5 meter cube, depth is 3.5 meter, and width is 5 meter. So before answering this question, one should have idea what is this settling tank, what is this discrete particle, what is width, depth of the settling tank, what is this overflow rate. So before solving this question, I will be giving you idea of what are those things. So first is the primary sedimentation time. So this is the first part of preliminary treatment. So you must have gone through. Sorry, there are different um, uh, treatment unit that is primary, tertiary, secondary. You must have gone through. So and there is preliminary treatment. So after preliminary treatment, there is the second treatment unit come which consists of primary treatment. The first unit where water goes after preliminary treatment is through in primary sedimentation tank. This consists of settling zone. So here you can see that this is inlet channel. So water after passing through the screen chamber and grid chamber, if you are treating wastewater and if you are treating groundwater, it will just from screening chamber it will go to this primary sedimentation tracks, and that water will contain some suspended solid. So what happen, our aim is to remove the suspended solid and that particle will be removed in this settling zone. So water will go from this inlet chamber, and there is baffle here because water will be coming with high flow, so it will just go directly into the settling zone. It might create a turbulence here, but our concept is we want our water to pass very smoothly with some constant velocity, yeah, that is constant horizontal velocity and constant vertical velocity. So what will happen that water will strike on this baffle, and from here the water will go here, and finally there will be some time where this water will stay here, that is known as detention time, and after that this water will go into the other unit of the treatment. So this is a plan view of if you are seeing from outside how this primary sedimentation tank will look. This is its different part. part. So the main function of this primary sedimentation tank is sedimentation means settlement, and how it is designed, the process in which suspended solid which is present in water, wastewater, are allowed to settle naturally by action of gravity. Here there means during this treatment we don't add any kind of chemicals, or just we let our water to pass through that settling zone. From name itself suggests that this is a settling zone where suspended particle will uh, where this suspended particle will settle down. So the second question is, are there different type of sedimentation? So yes, there are different type of sedimentation. So depending upon the where particles are getting settled. So what is happening currently? We are looking at the primary sedimentation tank, where what we see that individual particles settle down without interfering other particles. Suppose there are, obviously there will be large number of particles in the system, but it is observed that, or it is assumed that in settling zone, each particle will settle on its own. No other particle will interfere in their settlements. So that's why it is known as type 1 and discrete particle settling. And this thing happen only in primary sedimentation tank. So that's why it's in question it was written as a discrete particle, as a discrete suspended solid. So from there, if from there, because in question it was not written in which treatment unit this management is being done. So how will you decide that for which unit I have to find its length? So from the question, first you should have idea of this discrete. So from in question it was written then that it is a discrete discrete settlements. That's why our first hint should be that it is talking about type 1 settling or discrete particle settling that is happening in primary sedimentation tank in settling zone. There are different kind of uh, set there are different kind of sedimentation also, that is type 2 or also known as Flocculant settling. In this happen in this settling, what happened that some of the smaller particle, a suspended particle bone settle due to gravity. So what we will do, we will add some chemicals, and that chemical will surround that suspended particle, and it will get heavy, and that will make it settle down. So you can see, if you read this statement, you can clearly see the enhanced settling involves adding some chemicals like coagulants and flocculants to promote the aggregation of particles into larger flocks. Initially it was very small particles. Now due to agglomeration, the particle has turned into larger flocks, and these larger particle will settle down, and in that way that the particle which was not able to settle down will be removed. So this happen in another treatment unit. Okay. So third type of settling is type 3 or hindered settling zone, in which in this type of settling, hindered settling is when particle in a group slow each other down as they fall through a liquid, making a process of settling taking longer than it would if particles were alone. So, from the name itself, it suggests there will be hindrance in the settlement of suspended solid. Last is type 4 or compression settling. So, what that a larger the particle which is larger, I would request you to please turn off your mic. Thank you. So in from the name suggests compression settling. So what will happen that now imagine there are larger particle and a smaller particle in your system. So larger particle will settle down, but a smaller particle won't settle down. So what happened that we add some chemicals, means not some chemical. Yes, we add some kind of chemicals, a bacteria via which what will happen that this larger particles will start settling down, and the smaller particle will this larger particle will settle down, it will also compress the smaller particle which is present in the system, and they both will settle down. That's why the name suggests compression settling. This kind of settling happen in tertiary treatment. If you will miss in upcoming lectures, you will look at all these kind of settling, but for solving our question, we would just focus on the discrete particle settling, where individual particles are settling on their own with the help of gravity. There is no interference by other particles, and this is happening in only primary sedimentation tank. Okay, so Hmm. So now, as I have said, I will be only discussing about the type one settling, that is discrete particle settling. So in this case, what happened that consider this is a concept of settling. So, now, as you can see that water will be coming here. It will also bring a suspended solid which will settle in this zone, and when the suspended particle will settle down, it will settle down with some settling velocity, and that velocity known as settling velocity. And that velocity known as settling velocity, and that settling velocity plays an important role in designing this sedimentation zone or this primary sedimentation tank. Remember why we are doing studying this. Our primary aim, yeah, main aim is to learn how to design this primary sedimentation tank. Whatever unit that you will be studying in this lecture, yeah, upcoming lectures, you should have an idea that how to design one primary sedimentation tank. Suppose if you are visiting some water treatment or wastewater treatment, you should have idea on what you will see. There is some space or some gap, water is flowing here from here and there, then you should have idea like why this has been designed in a such a way. So so the our aim means our main aim is to understand any design which is already established, yeah, any power plant which is already there in existence, or to design some new power plant, new treatment, sorry, not power plant, treatment plant, water treatment plant. So our we know that this will settle with some velocity that is known as settling velocity, and that play an important role in our design of this primary sedimentation tank. So before going to the design of this primary sedimentation tank, one should have an idea that what is this settling velocity. Now just imagine this is a suspended particle and it is in water. So there will be three kind of force acting on this particle. First, the weight of this particle, its own weight, and that will be given by 4 by 3 pi r cube into its density. Similarly, there will be a buoyancy force that will be exerted by water on the system, and that will be given by 4 by 3 pi r cube into density. And finally, there will be a drag force, and drag force is given by 1 by 2 coefficient of drag coefficient into density of water into velocity square into area of projection. So this will now this consider this as this particle have a radius of r and diameter d. Okay, so d will be r will be d by 2. So drag force, you should have miss these are the basic formula that everyone know. Now I will use all this concept to derive the settling velocity formula. So now what will happen? There will be a time as soon as water will enter the settling zone. There will be a time that will be called as equilibrium time, where what will happen that all these force will be in equilibrium. That upward force will be equal to downward force. So if we equate it, this drag force will be equal to the weight of this particle minus whatever the buoyancy force is there on the particle. And if we substitute all the value, what will happen that we will be getting this equation. So I will take the volume of this is 4 by 3 pi r cube is the volume of that suspended particle. I will take that thing common, and this r square this r square, the area will be substituted by pi r square, and this r square will get cancelled out, this pi will get cancelled out, and we will left with this equation. And we know that density of water is a specific density divided by acceleration due to gravity, and the radius is d by 2. So we will be putting this value here. So after, if I put all these value here, here it will be one, we will be getting this equation. And now we also know that gamma s by gamma w is also referred as gs, that is a specific gravity of that solid. Here we are here we are specifying density of the solid with respect to density of the water, and that is being represented by gs, that is a specific gravity of that solid. Okay. So and we know that at equilibrium velocity will be equal to settling velocity. So I will be putting this value here, and if we equate it, we will be getting this kind of this kind of equation, that is Vs is equal to under root 4 by 3 G. Oh, I missed one unit here. It will be, there will be one G. It will be G into D. Okay. Sorry for the mistake. So from here you can see that this g will go there, 4 by 3 will be remain as it is, cd will be go downwards, and gs minus 1. There is one more mistake. Sorry for the mistake. Hmm. 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 So our final equation will be this. So this is a general term for settling velocity. Now now there, we know that there are different type of flow in our system. So there are generally three kind of flow: laminar flow, and other flow is known as transient flow, and the third type of flow is known as turbulent flow, that you will be studying in fluid mechanics. If you are not aware of it, then no problem, you should know that. Now you will know in the future. So now consider the first flow. Now if you I have discussed that in when water is going to the settling zone, it first strike the baffle zone. Baffle in the, I will just go through the picture once again. So see what will happen, that here the water is coming in a very turbulent flow. That's why and if I pass directly into the settling zone, what will happen, that some particle will get settled down, some particle will just scattered out here and there, it might won't get settled. So our target is to pass our water very gently into this system. Please turn
अरे
off
यार
your
ये कौन
mic.
सर पढ़ा रहा है?
Please turn off your mic. Thank you. If you have any question, you can ask by raising your hand. Huh? So the reason for adding baffle is that we want our water to pass in the settling zone in a very smooth way. Okay. So coming to the point which I was discussing. So in this way, what will happen, that our water will pass smoothly in the settling zone, and this flow will be laminar flow. And the condition to identify a laminar flow is given by Reynolds number. Reynolds number is given by density into velocity into diameter divided by dynamic viscosity, and it should be less than equal to 1. So suppose if you have given some for a flow, if you all this data has been given to you, you can put the value, and if that value is less than 1, you can say the flow is laminar flow. And in this condition, the density diameter of your solid should be less than equal to 0.1 mm, sorry, 0.1 mm. And there are two way to represent this Reynolds number, that is in respect to that dynamic viscosity and kinematic viscosity. The relationship between, you can relationship between this u mu and v is v is equal to mu by density of that particle. Okay. Hmm. So now what we will do that, and there is as per Stokes law, the drag coefficient is given by 24 by Re. This is formula which is given by Stokes law, and here we will put the value of Re, and Re we will putting the value of this Re here, and either we can put in the terms of dynamic viscosity and kinematic viscosity. And if we substitute this CD value here, we will getting the settling velocity in this manner, that Vs is equal to Gd squared Gs minus 1 18 mu, sorry 18 V. Mu, I don't know what this term is called, so I am just calling it V. But remember, this is kinematic viscosity. So now you are aware of this formula. So this settling velocity is for our settling zone. I am just out of this is not related to primary sedimentation tank. Suppose now in some other treatment unit, yeah, at some other places, your flow is transition flow. At that point, RE will be you will be putting the value of all these value, and you can calculate RE, and if it is greater than equal to 1 or less than equal to 1000, then that will be termed as transition flow. And here the diameter is of range of between 0.1 and less than equal to 1 mm. And here this is coefficient in transition flow, the drag coefficient is given by 24 by Re plus 3 by under root Re plus 0.34, that is equivalent to 18.5 Re to the power 0.6. So this is related to something else that I have given you extra information. But for our settling zone, we know that there is a laminar condition, and this formula will be used for our design purpose or calculating the settling velocity. So so the overall there is settling velocity, means this particle will enter in our settling zone, and it will settle down at this velocity. And there is second type of velocity that known as scoring velocity. So now what will happen, that your water is flowing at some speed. What will happen, that the particle which has been settled, there is a chance that it will also particle will settle down also, and it will move in the forward direction also. Remember, till now I was just discussing that particle will just settle down. I was not discussing that particle is settling down also moving out. But it is seen, it is means common sense, like if something is falling in the water, it will just go down and it will also move forward. But and at what rate that water that solid will move forward is given by this formula, that is 4 under root G. You can see that this is similar to this thing only. This equation only, and by dividing it by GW, I have represented in GS minus 1. Okay now. So here this equation can be also written as 4 under root G GS minus 1 into D. So if someone has given you all these value, you can calculate Vs and Vsc for any flow for any particles. So now there are, means this is in general what happened. See, all the wastewater consists of organic matter. Inorganic consist of mainly organic matter and some inorganic matter. So they have specify that in many books or in many research paper, you will see that G for wastewater is around 2.65. This gravity is acceleration due to gravity is fixed 9.81. Density of the water and particle is 2650 and 1000 in kg per meter square. And viscosity, remember this is kinematic viscosity, and that is given by meter square per second. So remember, when you should use kinematic viscosity, suppose if you are if you don't know, if you are not knowing that this you will be given some question and you will be asked to calculate the settling velocity. So here what is happening, that as I am using mu, so sorry, I am using v, that's why there is no multiplication of density here. And depending upon the type of question, or depending upon the depending upon the given unit. Currently, what will happen that most of the time you will be given kinematic viscosity that has unit of meter square per second. So you will directly substitute and you will get your answer. But the unit of kinematic viscosity is in terms of Newton and all this thing. I will request or I will suggest, please go through the unit of both. You should know the what is the unit of this dynamic viscosity and kinematic viscosity. Means in general you will be finding the unit of this kinematic viscosity, but you should have idea of both the viscosity. So now the coming to the design part. So remember, whenever we design, there should be some objective. So during design of our primary sedimentation tank, our objective is to remove the particles that are up to 20 size, and I have to remove that particle completely from my water. So this is objective of primary sedimentation tank. So you can say that why not below that, because then it has been seen that if we try to remove the particles which has size lower than 20 the efficiency of primary sedimentation tank will be very low. So it is always suggested that we should work in a such a way, because we know that further there are some other units are coming that will help in the removing of suspended particle. So why to put burden on all the burden on one unit only? So we want, when we are removing suspended particle, we want to remove some of the suspended particle initially, and the remaining particle will be removed in upcoming unit. So that from you can refer to any book, Indian author book or foreign author book. There you can see that in primary sedimentation tank, our aim is to just remove 20 size completely. So you can calculate the scoring velocity and this settling velocity by putting size. If we are talking about size, then it is diameter of the particle, and we know the all the general value. These are the general value, and we can put it here, and you will be getting the value. Vs scoring velocity is 0.72 meters square per second, and settling velocity is 3.56 into 10 to the power minus 4 meter per second. Sorry if I've told unit, its unit wrong. It will be meter per second. So coming to the next, now we are confirmed that what will be our objective of the treatment plant, and we also know that this uh, depending upon the with the help of our objective, the setting velocity will be this thing, and scoring velocity will be this much. So there is already I've said when I was discussing about primary sedimentation time. What is the detention time? Detention time is average flow for which water stay in the sink, and that is given by V upon volume of the tank divided by flow at which water is coming to the settling time. So unit of V will be meter cube, and unit of flow will be meter cube per second. Meter cube will get cancelled out, and you will get your time in second. Yeah, whatever the unit of this q is there. And there is one term defined as surface overflow rate, that is SOR, and this is given by at what flow rate the water is coming and what is the surface area of this tank. So a tank will be have length, some width, and length, some width, and then some height, and the length and the width will corresponding to the area of the surface tank. So from there I can calculate what will be the SOR. In for design SOR, generally you will be given that what for what flow rate you want to design your tank. So generally it is taken. I must have written down. Sorry. Mm, Generally it is taken between 30 to 25 to 30 meter per second. And remember, the if I am saying meter per second, but the unit of this SOR is given now. See this thing, this is meter cube per second, and this unit of this has meter square. So the unit of SOR is generally written as meter cube per second per meter square. Okay. I hope you are able to understand what I am saying. So currently I am discussing that how to design a primary sedimentation tank. The first step, you will set your objective. You will calculate different kind of velocity. This SOR will be given to you, and you will consider length of L, width V, and the depth will be D. So what? Now you will also know, miss, Q will be also known to you, miss, at what, because when we are supplying water to our sedimentation tank, we know at what flow rate water is entering our settling zone. So from here, we will uh, we will uh, we will try to know our length and breadth of our, means, area of our sedimentation tank. And from detention tank, from detention time, so these all things are controlled, means, how, for how much time I want to uh, I want my water to stay in settling zone. These all things are pre-fixed, means, means there has been several uh, 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 construction of treatment plant, and all these things are predefined. So the only thing which you have to calculate is length and breadth, depending upon the different condition of your different condition of your wastewater. So from this detention time, I will be relating the volume divided by at what flow rate it is coming in the our system. And you know that this whatever we will be the whatever will be the our settling velocity, that will be equal to flow rate and the surface area of this our suspended solid, sorry, surface area of our sedimentation tank. So means, we also assume, and it has been seen that in rectangular sedimentation tank, the critical velocity is always numerically equal to the this surface flow rate surface flow rate. So now what will happen, that you are aware of your surface flow rate, and you are aware of your settling velocity. So now what you will try to do, that you will try to make in keep your L and B in a such a way that these these velocity are equal, and to make sure that all the suspended particle which is there in the system get settled down. So so if we put all these value here, you can calculate the value of SOR. And from there, and also see, I already tell that generally SOR is defined as 30 to 35 meter cube per meter square per day. Just remember it, as I have divided meter cube per day per per meter square. That's why unit is written in this way. Never write the unit of SOR as meter cube, meter per day, or meter per second. So whenever you see somewhere you are seeing that this kind of unit is there, just remember that if they are talking about mm, this SOR, that is surface overflow rate. Now you also want your suspended particle to don't go away from the settling zone. Suppose if particle has settled, that remains there. So how will you make sure that that particles remains there only? So for that, you should make sure that your horizontal velocity is less than this scoring velocity. So for that, and for so for that cases, for that case, what we want to do, that our horizontal velocity should be less than equal to this velocity. In this way, what will I will be making sure that all suspended particles settle down, and it do not go further into next unit, or our aim is not fulfilled, which was to settle down 20 mm size. So with the help of this VS, we will have an idea of L and length and width, and from the with the help of this horizontal velocity, we will have idea of this width and depth. So the main so if some data has been given to you that you have to design this kind of settling zone, by following this step you can find out the length and width of your settling zone. I hope this is clear to you. The main point is that these two units, these two velocity are important. This velocity makes sure that scoring velocity makes sure that all the particle which settle down in your system remain in the system. It doesn't go further, and this velocity makes sure that all the particle get suspended in your system. uh, it is calculated with the help of the formula which I have discussed earlier, and it is also depend upon this length and width of our settling zone, and the horizontal velocity depend upon how width and the depth of our system. I hope this is clear to you. This was a this see, if you miss, I am discussing it in a very short way, like I'm trying to explain it, but these are not this short. If you go if you have go, when you will be studying in your department the design of primary sedimentation tank, they will take around 4 and 5 hours to explain each and everything, why we are assuming this thing, because these things are very rigorous thing, like you have to do what will happen that initially when you will calculate, you will get depending upon your condition, you might get this SOR very high, so you have to do such thing that this SOR get reduced. So and also if you study from different person, a different teacher, they the basic concept will be for everyone will be same, but there will be some variation. So I am just giving you idea how to design, means how this primary sedimentation is being designed. So for more detail you can refer to the book which has been suggested to you. Okay, so I will be moving forward. I have already discussed what is this settling velocity, scoring velocity, a concept of some concise concept of how this design, how to design a primary sedimentation tank. So coming to the our question, the see, you should understand the language of the question. If you understand the language of the question, then you will be able to answer it very easily. Just ignore the first part. It is just saying the discrete suspended particles. This discrete is itself explanatory. The question is giving itself a hint that you have to use the velocity which is used for discrete particle. And we know that for discrete particle there will be, we will use the Stokes law, and here there the formula which will be used will be given by this term, that is Vs equal to 1 by 18 this GDS square into GS minus 1 divided by 18 kinematic viscosity. So a question, a very simple question is being given to you, that overflow rate is 18.6, depth is 3.5, Q is equal to 720 meter square per second, and width is 5 meter. Okay, so the SOR which is given by 16.5 meter per day, that will be equal to Q divided by L into B. So remember this, during design I said that this SOR is given by Q divided by length into width of your sedimentation tank. Length and width is given to you. Length is, see, length you have to calculate, width has been given to you, width is 5 meter, and if you put the value, you will get L is equal to 8.73. See, in this question there is no need of there was no use of depth of depth of what do we call depth of settling zone. So this question, this data was given just to confuse you. Only there was use of this width, that is B is equal to 5 meter from here. So the our final answer will be the length of rectangular tank designed for removal of discrete suspended particle would be 8.73 meter. I hope this is clear to you. If you have any doubt, you can raise your hand, or else I will move. See, there might be something which, if you feel that I'm saying something which is wrong, you can object me. Okay, now I am also a student, just first year PhD student. I have completed my master last year, so there might be something which which I will try not to speak anything which I have not, I don't know. Whatever I am saying, I have studied from some book here somewhere, and I am trying to convey you that. But if you still feel that no, the thing which I am saying is wrong, you can object me, because so it's just kind request that if you think that I am speaking something wrong, just object me there or correct me. I will just see. I will give attention to you whatever you are saying. Okay. And if you are not willing to share that this thing is wrong, so wherever you feel that thing is what am I saying is wrong, just go check by yourself. Go to some standard books and check there. Okay. But be assured that whatever I am saying here is 90% correct. I won't be saying something wrong to you, because this thing will be uploaded on YouTube. Everyone will see it. So this will be a insult to me, or someone can raise question why you are teaching if you don't know. Okay. So the coming to the second question, the following data are given for a channel type grit chamber. So here the new sedimentation, new treatment unit come, that is grit chamber. Grit chamber is generally before this primary sedimentation tank. Okay. There are two questions related to grit chamber. This one is numerical question, and the other one is subjective question. So first I will discuss the numerical question, because the concept here applied is similar to what happened in sedimentation tub. In this grid chamber also, what will happen, that particle will settle as a discrete particle. Each particle will settle on in a independent form, and in question itself is written that a Stokes law apply. If a Stokes law is applied, you have to think of laminar flow. CD is equal to 24 by RE. Sorry for that. So just read the question, what they are giving, what kind of data has been given to you. From that thing you can just take an idea that yes, they are asking about a Stokes law, then I have to think about laminar flow. That same formula, Vs is equal to under root GDS square, sorry, V is equal to GDS square GS minus 1 divided by 18 mu. As simple as that. Okay. So read this question. Length of 10 meter is there. Q is 0.75 meter cube per second. Depth of the wastewater at peak is 0.8 meter. Width of the channel is 3 meter. A specific gravity is this thing, and you have to find the max diameter of the particle. So see, they have just given some random data, and they have asked to find the diameter. So if you have gone through the design is similar to what I have said in the primary sedimentation tank. So here this uh, settling velocity will be given by flow divided upon length into width. What is the flow? Flow is 0.75 meter cube per second, and it is 10 into 5 meter square. So it will be 0.025 meter per second. Okay, I think hope this is clear. And as per Stokes law, see, as per Stokes law, we know that Vs is equal to rho g gs minus 1 ds squared 18 mu. See, this formula is different from what I have derived. It's not different. Here I have used kinematic viscosity. In that formula, I have derived with the help of uh, uh, this is dynamic viscosity, and during derivation I have used kinematic viscosity. And you should also pay attention that what kind of data is given to you. In this question they have given me dynamic viscosity, and see, the unit of dynamic viscosity is Newton second per meter square. So from this you should apply your common sense, and you should you should say that this formula will change. There will be a multiplication of this rho, that is density. We will put all these value. 0.05 meter square density will be 1000 kg per meter, kg meter kg per meter cube, 9.8 meter per second square, 2.5 minus 1 d square, 18 into 10 to the power minus 3 kg per second. So this kg will cancel out. This second and this second square will get cancelled out, and what will be remaining, this meter and meter, 1 meter will go, so meter square. So from this calculation you will be getting your d as in meter. Remember, always play with units. If I won't have written my units, I might have confused that in what unit I will be getting my d. So always make sure that to write units. So if we put all the value, you will be getting 1.75 into 10 to the power minus 4 meter, that is equal to 0.175 mm. Okay. So the answer to this question will be 0.175 mm. Then now just imagine that your unit is kinematic viscosity. Sorry, kinematic viscosity. Kinematic viscosity. Then what will the unit here? The unit here will be meter square. What will be the unit of kinematic viscosity? The unit of kinematic viscosity I have written here. It is meter square per second. Okay. So here, so this will be in meter per second square. This will be this will be meter per second square. This will be meter square. This will be unitless, and this again will be meter square per second. So this meter square will get cancelled out, and this second square will get cancelled out. You will be getting the unit of velocity as meter per second. I hope, just try to relate each and everything, then you will have a clear idea what is going on. Just by remembering the formula you might forget, but if you just try to relate the unit at what in what condition what things are used, then there are high chances that you won't remember, you won't forget your formula. Miss, for me also, whenever I see this formula I remember that, see, if you in mind you should know that the formula is something g minus 1 d square, something like that. If you have forgotten it, whether it is d or d square, just substitute the units, and for substituting unit you must know the unit first. Okay. So this will be d 1.75. This is final. This is this is this is the final answer. You have to report your answer into 0.175 mm. Okay. Coming to the third question, that is objective question. Which of the following factor does the sewage load on not depend upon? That's uh, sorry, for the, I think question language a little bit misunderstood. The question is that out of all these four, obviously, what happened that we produce sewage means they are talking about wastewater are being produced. So on what factor that it does not depend. Okay. So before discussing also you can answer this question. If some waste is being produced, if some wastewater is being produced, it will depend upon what? It will depend upon the population. Means how means who is producing it, because most of the wastewater is being produced by human only. All the wastewater is produced by human only. So it does not depend upon this the what is my treatment plant is there to treat our generated waste. It don't know how, it has no control on how much waste is being generated. So before discussing you can answer this rate of water supply. Of course, how much water is being given to you, obviously it is said that out of 100% water we waste around 95% of water. If you want to see that how much water you waste, you can do a simple experiment, a simple task. When you are brushing your teeth in the morning, just keep a bucket below your tap, and you will see that for just brushing and just for cleaning your teeth, how much water you are wasting, and it will come around 10 liters. So for a simple, it won't, I am talking in the maximum. So you will see that you have collected around 10 liter of water just for brushing your teeth, cleaning your teeth, washing your face. Obviously many people when they clean their teeth, they generally wash their face also. So if you keep a bucket below your tub, below your tap, you can observe this is a simple this is simple task that is given to us when when I was studying this topic, that how much water we waste. Just you can check by just simply placing a bucket below your tap when you are brushing your teeth. Okay. So rate of, obviously why I'm wasting too much water, why I'm brushing, why I'm cleaning out, because the water is being supplied to us. Population, number of population is more, there will be more wastage. Infiltration of groundwater, infiltration of groundwater, this is indirectly linked, means how much water is being infiltrated in groundwater. But somehow this also affect our sewage load. Design of sewage system, it does not affect, means it has no link on how much wastage is being produced. It is just to treat our wastewater. Okay. So again, miss, see, by this was some basic, basic common sense question. There is no hi-fi science in this thing. There should be some problem in option D, but you can imagine that suppose in a area water is not water is being infiltrated in groundwater. So the sewage, the waste which will be produced will be, wastewater which will be produced will be less. uh, this is a common thing. Still, I will discuss what is this sewage load. The sewage loads refer to the amount of wastewater or sewage generated by particular source, such as community, household, industrial facility, over a given period of time. Whatever waste we generate is known as sewage load. It typically includes mixture of domestic wastewater from toilet, sinks, showers, and laundry, as well as potential industrial wastewater from manufacturing process or community activities. So I think this should be clear to you. What is this wastewater? Out of context, I am discussing something. See, my aim is to give you some, to discuss some idea and to give you some concept of some, give the concept of something new. So we know that wastewater is produced in domestic thing. Okay na. So domestic wastewater can be also of two type, and first one is referred as black water, which is toilet water, and this is mainly organic in nature, and which in that waste there is high percentage of carbon, nitrogen, phosphorus, and macroorganism. This is known as toilet waste. And the second kind of wastewater which we produce in our domestic setting means domestic house, is kitchen waste, which is also mainly organic plus other thing also. Okay, now kitchen waste, washing and cleaning waste. Okay. So toilet waste is different from the kitchen waste, and that is being referred as black water and gray water. Okay. So this one contains all kind of waste, organic also, organic from the kitchen waste, and this weeding and cleaning waste will produce some kind of dirt, soap waste, and all these things. So combining all these things, that is black water plus gray water, is known as domestic water. Okay. I hope this is clear. To this was a knowledge I was discussing about this sewage load. So I thought that you should know this. What is this black water and gray water? Anyone can ask you if you are appearing for any interview or in environmental field. I have already discussed this primary load. Primarily depends upon this thing, rate of water supply, result in more water generated. More water will be given to you, you will produce more waste. Population growth, infiltration. Well, while filtration can affect the volume of water entering the sewer system, it does not directly affect the amount of organic waste and pollutant in the sewage. This is what I was telling to you. Hence, the design of This is of my final conclusion that correct option is D, that is sewer of design. It does not, whatever waste we are producing does not depend upon the design of the sewer. I hope this is clear to you. I am going to the question number 4. Four is multiple correct question, and the question is select the correct statements regarding a screen and their purpose in the wastewater. See, actually, every day at this time I face a network problem, so it might happen that after 5 minutes, yeah, 10 minutes, you might get disconnected, or my net there will be a net issue. So please rejoin using same link. Do not, if you think I am giving you some important knowledge, please do join us. Please do join using same link. Okay, now because in last two session it's happened that there will some network issue and meeting was over, but meeting was not over. There was some, so I am reminding you, miss, I am telling you earlier, miss, in in advance that this problem will come. Hmm. So the select the correct statement regarding the screen and their purpose in the wastewater treatment. So a screen, before answering question, you should know what is a screen or what is screening. So the function of screening is, first remember, this is preliminary. This is a part of preliminary. See, every unit is a part of either preliminary treatment, primary treatment, secondary treatment, or tertiary treatment. So if someone is saying that they are talking about this screen, so you should know this they are talking about preliminary treatment. So preliminary treatment, what we do, we remove boulders, yeah, large size particles. That is the function of our screen chamber, yeah, screening. And screening terms also suggest that, suppose you are also, this question is this term is generally used in examination, that they are screening for this job, means they are just uh, removing which are not suitable for further treatment, or that might hinder in the further treatment. Okay. So function of a screening is, screening prevents interference to treatment by removing large debris such as sticks, plastic, and other solid which could otherwise disrupt or damage downstream treatment process. So we know that this what will happen, that there is a baffle type of system. It will keep rotating. It will keep circulating on a chain. So you can search on YouTube what is YouTube, what is a video of a screening chamber and how the screen. You will see that water is coming, it contains some kind of material, sorry, it contains some kind of this kind of things, and there will be a steps like chain, and it will keep rotating from in a circular way, and whatever the this kind of particle will get on those steps, and it will get removed on the other side of, there is some separate arrangement is made where all the particles is being kept. Okay. So this is the primary function. And why we are removing it, see, we know that um, this primary sedimentation tank has to remove the suspended particles. So if we try to remove all the suspended particles in that primary sedimentation tank only, then it will just increase a burden on primary sedimentation tank. So every unit has some function, so that the upcoming treatment unit works in a very smooth way. Okay. Screens are indeed used to protect process equipment such as pumps. So now what will happen, that we know that we have to maintain a flow. So now just imagine if your wastewater contains some kind of some kind of this kind of particles, so obviously it will affect your pump. So we pump and different kind of pipes are there, so we want to save that also, because see, we do not design our treatment plant daily. We invest too much for a one time, so that it can it can keep working for many years. So that's why we try to remove all these particles. Okay, so this is, remember, consider this is as a, how to say, this screen chamber is going inside this thing is inside the plane. Okay na, so water will be coming here, this will keep rotating, particles will get collected on these steps, there will be some kind of a steps, and it will removed, there will be some arrangement made here, yeah, here, that will remove your screen, that will remove your larger particles. So what will happen that here the the water will be coming from pump, and it will be coming with the velocity u. And what will happen that when it will go on the other side, there will be decrease in velocity, because we are we are here we are somehow controlling our flow, so that the further treatment unit does not get disrupted by large amount of velocity. So obviously initially there was u velocity and final velocity is v, and which is less than initial velocity, so means there will be some kind of head loss, and that head loss is given by kg by 2g v square minus u square. So I am not going in the detail of this thing, but I am just giving you an idea. Yes, there is some head loss in the system due to this screen chamber. Actually, we are providing this facility, this thing, so that water can flow smoothly. So what were our option? Sorry. What were our option? Select the correct statement regarding the screen chamber. Screen prevent any interference to the treatment. Yes, this is correct. Screen chambers are used to protect process. Are used to protect process equipment. Yes, this is also correct. We don't. If suppose bigger particles go in a further unit, it might get. Sorry. Uh, if these kinds of particle will go in the unit which is not there to treat this kind of large particles, then it obviously it will get damaged. Screens are a part of secondary treatment. No, it's not part of secondary, it is part of a preliminary treatment. There is no head loss when sewage flows through them. This is also incorrect. So only correct option is A and B. Okay. See, I am just giving you an overview. If you want to go in detail, please refer some books. I will also, in the end, I will just share some book where you can read in detail. Okay. So the coming to the fourth question regarding this grit removal. Already answer has been given due to some animation problem, but let's move. Grit removal. So before knowing grit removal, you should know what is this grit. Grit removal. What is grit removal? Grit is coarse particle. See, a screening chamber was removing a larger particle. Then there is a called coarser particle, which is neither too fine, neither too big. That is in between. Okay, coarser and between larger, and between between larger particle and between the finer particle, we get coarser particle. And what does this grit chamber do? The grit chamber is used to remove inorganic particles up to 0.2 mm in diameter. Okay, so this is a plan view of grit chamber. What will happen that after from a screening, water will go in this grit chamber, and you can see this image is from we are looking from the above. When I was showing you the settling tank, I was showing from the side way, but this one is from above. So you can see that this water will go in a kind of settling zone only, and all the grit will settle down at the bottom, and it will be removed from side, and the water will go in the another treatment unit. treatment unit, and you can see that. Mhm. Yeah, you can see that this is a grid which gets collected after in this grid chamber. Okay. Hmm. So you have to in say in this question you have to select incorrect statement. The a in aerated chamber, there is no moving parts below the water surface. Of course, there is no moving part. All the things are stationary. So this is a correct answer, and this is a correct statement. And we are asked to choose incorrect. So this won't be our answer. A grid chamber is usually installed after primary sedimentation tank. No, we install this before sedimentation tank because we don't want any burden on our primary sedimentation tank. Primary sedimentation tank has some other function, that is to remove finer suspended particles. Okay, so this statement is false statement, hence this will be our one of the answer. A grit chamber are used to remove oil and grease from the wastewater. No, this is only used to coarser particle. Oil and grease is removed in another treatment unit. So hence this is also incorrect statement, and hence our answer. The purpose of a proportional bear at the end if the channel is removed is to measure the flow rate and yes. So I am not discussing about this proportional bear. So what happened that at the end of this grid chair there is bear type structure, proportional bear type structure. If you are not aware, I will suggest you to go to internet and search about this term. So you will see a nice picture in a rectangular channel. There will be a triangle thing in the middle, and some water will flow through. And this structure helps in maintaining a continuous flow rate. uh, this helps in just wait a minute, I will show you one diagram how this is how this great chamber. So these are my when I was studying in master, I have done this course in very detailed way, and their sir has discussed this. Just let me check where it is. I'm not able to find it. This is a proportional beer. We know beer. Okay, now. So here what happened that we this is used to maintain this is used when we want to maintain our desired flow rate. So this I will request you to please go through. Please search about this. You will there see what kind of equation is used here and what kind of terms are used here, and these all are used to design for designing our different part of sedimentation treatment unit. Sorry. Hmm. Okay. If anyone have any doubt, please ask now. Else I will go to the next question. Okay, no question. So coming to the next question. For a grid chamber, a flow velocity is 0.45 meter per second and detention period of 45 seconds. Length of the tank should be. I will request if anyone is interested to solve this question, please solve it. I will give you 2 minutes based on the formula which I have said earlier. If you want to, this is very simple question. Still, I will request you, for hint. I am just giving you, use this diagram. This is the length. Water is going from here to there. Obviously, water will stay here for some time. Then it will go in the next treatment unit. So, based on this concept, please solve this question. I am giving you 2 minutes, and you can write down your answer in chat box. If you are not solving, then you can say also, Miss, I will move forward. But if you are just solving it, please let me know so that I can wait. Flow is given to you, detention time is given to you. You have to find the length of the tank, and only thing is, there has been discussed. I have discussed many things, but I am just giving you a hint. Use this diagram: length, time, and some velocity. So what will be the length? You have to move from here to here at some velocity, and time required is given to you. So what will be the length? Anyone? Okay, so I don't. Okay, no problem. I hope you are able to understand. The problem will arise at that time where you are not able to understand what I am saying. There might be some my language problem. My English is not so good, but I am trying to explain in as much as sim- in a simpler way. Okay, so this was our great. This was our chamber. Water was coming from this side, was going through it, and it was crossing. It was staying from for there for some time, and it was moving at velocity v for length l. So this was very simple question. We know that velocity is distance upon time. It has to go, it has to travel a distance of L in some time. That time is known as detention time. All value has been given to you. You can find the length equal to 0 to 20.25 meters. So see, this was a simple question, and if you start applying the concept, if concept which has been, this was very simple question. Just remember, just you should know how to use the given data. If you start confusing flow velocity is given here, I will start applying this Stokes law and this settling velocity formula. There is no need. This is simple question. Just apply formula. I was giving you hint also that I have to travel from here to here at this velocity. So this question was very simple question. So the length will be 20.25. So this is an interesting question. Again, I would like you to solve this question. For a given discharge, the efficiency of sedimentation tank can be increased by. I have said this. I have used this term efficiency, and how I have used. There are four options: increasing the depth of tank, decreasing the depth of tank, increasing the surface area of the tank, decreasing the surface area of the tank. Okay. So the concept by efficiency was that means how we define efficiency means there is some given value. There is how we define our potential, our efficiency. We have some potential, say 10, but if we are doing only, if we are utilizing only 50% of 5% of 50% of our potential, that is 5 part of our potential, then our efficiency will be 5 by 10, that is 50%. Okay. So similarly to that, in a sedimentation tank, what is happening that this is our settling zone. Many particles will be coming. Now that particle will have some weight. Suppose x weight is coming, and out of these whatever the suspended particles are coming will have settled down here. So what will be the efficiency? Efficiency will be 100%. Why? Whatever suspended particle is coming from this inlet channel is getting suspended here, is getting settled here. Means means our efficiency is 100%. So we define the term efficiency, which is given by neta, that is weight of particle settled divided by weight of particle entered. So in this way, we can say that if all the particle which is getting which is entering there has settled, we will say that our efficiency of our sedimentation tank is 100%. If everything if it's not settling, then we will say that our efficiency of our sedimentation tank is not 100%. Okay, now generally in theoretically purpose, it is seen that it is never 100%. It is never that whatever suspended particle is entering in our system is getting settled down. There will be some suspended particle which will move forward with the flow. That depends upon the many factors, like horizontal, how much horizontal velocity is there and all these things. Okay. So from this I can say, so how much particle will suspend depends upon two things: settling velocity and the detention time. For how much time you have kept your suspended solid in the sedimented settling zone. If you are providing sufficient time, then obviously it will settle down. And with apart from detention time, sorry, I mismatched it, I said it wrongly. So miss a particle is is entering our system, and what is its settling velocity will determine whether that particle will settle down or not, and for how much time that particle is there in our system will also determine whether that particle will settle down. Suppose detention time is very short, water is coming and going, so what will happen? It won't get settled down. Okay. So it's depend upon the settling velocity and the detention time. So first I will discuss about this settling velocity. Assume in question it is written that in question it is not written that we have to assume something, that our discharge is constant, or obviously discharge in settling, whatever water is coming in this settling zone will come with some constant velocity, constant flow. Okay. So assume, we know that yeah, we can assume that flow is q, length is l, width is l of pst, which is constant. It's not changing with time. Obviously this length and width cannot be changed, and we have already fixed our flow with the help of this grid chamber when it was passing through that chamber with the help of proportional wear. Okay. The critical velocity is the settling velocity of a smallest particle that will completely removed in the pst. This thing we also know with the help of ps. Now just we design our suspended particle in such a way that now we design in such a way that if suppose a smallest particle is being able to settle down, so obviously the particle which is larger than that uh, larger than that particle will obviously settle down. So the critical velocity or settling velocity is the settling velocity of the suspended particle that will completely settle down. And we know that this Vs is equal to SOR and given by Q divided by L cross B. L cross B. So now in this question, in this equation, does um, mm, hmm. So from this equation you can say that Vs is not function of depth, and we know that Vs is used for uh, Vs is used for calculating this length and width. But Vs is not function of depth. Hence, hence we can say that for pure settling condition, depth of PST has no effect on PST efficiency. PST means primary sedimentation tank efficiency. Is this clear? Now, as this thing is from this analysis, we can say that this depth is not important in its design. So another question is that can we make it very large or very small? Depth is not so important in designing. Then what should be its ideal range? There should be some range, or either we can make it a small or we can make it as large as we want. In price, no, there are some limitation in giving the value of d also. In practice, what happened that the depth is kept between 3 to 4 meter. There are several reasons. Obviously, the question is why. Uh, I'm answering two questions. First question is if depth is not important in design of sedimentation tank as settling zone, then can we keep our depth as deep as we want? If not, then why? And the second, in other form, the same question can be asked that in practice, what is the depth of this primary sedimentation tank and what is its range? The range is 3.5 meter. Reason why we are keeping 3.5 meter, I have written down it here. Assuming flow length and breadth of the PST constant, provision of the lower depth will mean the horizontal velocity VH will be high. Now just remember, this horizontal velocity depend upon the B and D, that is depth and how much what is the breadth of the that sedimentation tank. So what will happen that this will result in very high horizontal velocity. Now just remember what will happen if our horizontal velocity will be very high. Our horizontal velocity should be less than our scoring velocity. If that is not the case, what will happen? All the settled particle will move away from our settling zone. Hence, higher the value of VH, higher the size of particle that will be scored. Hence, the settling tank efficiency goes down when D is low. Hence, the minimum depth provision hence the minimum depth provision is, hence there should be hence it is said that there should be some minimum depth and that is kept at 3 meter. Okay, a shallow PST will susceptible to wind effect, and the calm condition required for PST equation cannot be maintained in the shallow tanks and when there is a steep breeze. Now imagine that your PST is very shallow. So what will happen? There will be some wind effect. Particles, water on the uppermost layer may face some wind effect. So that's why it is said that we have to keep our length 3 to 5 meter. Now this was about settling velocity. The second thing which on which our efficiency depend is detention time, and it is defined as every time that a particle suspended in the settling basin can be calculated using the direct formula, and that is given by volume divided by flow. This formula is very clear to you that our settling zone has some velocity v. It will remain there for some time, and that can be calculated with the help of volume divided by what is the at what flow the water is coming inside our system, yeah, going from our system. So that's why detention time is given as v by q. And now volume is the function of length, breadth into depth, and this L into V is given as area. So volume is area into D, and we know that in for efficiency D doesn't matter. This I have already said. So hence the Q, if the Q is constant and if we increase the surface area of the tank, the volume V will increase accordingly. Therefore, the detention time will also increase because the flow rate remain constant. Now, suppose if you are increasing the surface area, this flow will increase. This volume will increase and increasing the detention time. And already said the more detention time, the more efficient, the suspended particle will get more time to get settled down. So hence the correct option will be C, increasing the surface area of the tank. Or in other word, you can say that by increasing the surface area of our sedimentation tank, I am increasing the detention time. I am increasing the detention time of my uh, detention time of my settling zone, and hence increasing the efficiency. So the correct option will be um, C, that is increasing the surface area of the tank. Okay, this is very simple question. What is the peak factor? The peak factor is everyone is aware of this. Peak factor is given by peak flow divided by average flow. Uh, this is related to water demand thing, like how much water is being given to you, and you must have been aware of the idea of this thing, what to be called 24, that's the maximum daily demand, maximum hourly demand, maximum weekly demand. So I won't I haven't not considered because this is very common thing. If you are not aware, I will request you to go through the some standard books. You will get a major things about this. But main concept is the peak factor is given by this peak flow divided by average flow. Okay. So coming to the one interesting question, when I was explaining this discrete particle settling, so what I was doing, that I was keeping a spherical. So any reason why I was keeping the particle spherical? So why it is why I'm keeping a spherical, I will explain later. But think about it before going to the answer. Obviously, I will give you the answer. But before knowing the answer, I want you to think about it. Why I have considered a spherical? There will three unit: drag force, um, this weight or this thing, buoyancy force. So use that concept and try to know that why I was using a spherical particle. And there are some other. If you are not remembering that formula, it's okay. Just think logically that why we have I have considered this as spherical particles. So why not rectangular particles? Or mm, hmm. Because in nature the particles can be of any type, not just only a spherical type. It can be of rectangular, square, because we don't know. There are many kind of suspended particles. Okay, just this was another thing. The question is, non-spherical particle will settle smaller, slower, faster, equal, or same as spherical particle. Okay, so during settling velocity, what I was saying that consider this particle of diameter d having uh, uh, diameter d, in a water, and in water there will be three kind of force, that is drag force, fb force, and weight of that, sorry, buoyancy force, and the weight of the particle. So the weight of particle is given by volume into density of solid, and buoyancy force is given by density of the volume into density of the water, and this drag force. So before going to the next slide, which contains the answer of this question, I want to you to think that if if consider volume to be same for all non-spherical. Suppose it has volume, a spherical particle has volume x. Sorry. Consider volume of this spherical particle and non-spherical particle to be same. If it is of x meter cube, then this is also x meter cube. So this the weight of the particle is same, buoyancy force on the both particle is same, density is also. What will be changing? We will be changing this drag force. How we will change? I said this answer. How we will be changing the drag force? Now read this. Non-spherical particle will have larger surface area to volume ratio compared to a spherical particle of the same volume. So it in a see, you must have studied in your 12th class, yeah, anywhere, that this spherical particle have least area to volume ratio. For apart from this spherical particle, every other shape has this area to volume ratio very high. That's why in nature, means our there is advanced not physics, there is physics behind it, that not physics also, simple math. You can just divide the area of a spherical particle, divided by its volume, and now compare with the cube shape, yeah, rectangular shape, yeah, cuboidal shape, yeah, any kind of shape. You will see that this has least area to volume ratio. Okay, and the reason to choose is a spherical because it will help in our calculation also, for calculation of our uh, for calculation of settling velocity. We assume that every particle is spherical in shape, because if we start trying to formulate formula for every kind of particle, then it will be very difficult to analyze our system. So in general also, if you are collecting 100 kind of suppose 100 gram of suspended particle, 90% of suspended particle will be in spherical form. It won't be perfectly spherical, but it will be entirely spherical in the shape. So as this spherical particle will have uh, a non-spherical particle will have larger surface area, and we know that this drag force is depending upon the surface area. So that is AP. AP was what was the AP for this pi r square, or this say projected area, you can say. So what will happen that the increased surface area result in more drag force acting on the particle as they settle down in the fluid. So this drag force will be very high for our suspended particles. That is non-spherical particle, because you have changed AP. Okay. So consequently, non-spherical particle experience greater resistance to motion and gets lower rate than the spherical particles under similar condition. Okay. So you can miss you can you can directly see that if you are if drag force is higher, what is happening, this means particle is trying to go downwards, but this drag force and this buoyancy force is trying to stop it, and now you have increased buoyancy force. So obviously what will happen, the velocity via which it was going, it will get slower down. This is just conceptual, this was just our imagination, yeah, common sense, that yeah, this will definitely slower down. Now if you want to check it mathematically, so for mathematically I will again refer to this equation doing this this derivation. You can see that if you are increasing this AP, because volume in all these three cases are same. So for a spherical particle, as I said, to make our calculation easy, I have kept this pi r square so that this can cancel out. Now just imagine you have kept AAP which is very high, and now you will do the calculation based on those things. So you will find out that Vs coming will be different or larger than as in a spherical particle. So you can miss, which is more simpler method. You can consider, for your benefits you can consider this as a cuboidal whose area will be a cube and area whose volume will be a cube and area will be a square. And remember, you have to relate this r with a, means volume of both, means if you are trying to this derive this equation that what will be the v, then you have to assume one thing, that volume means volume of, suppose a cuboid has length a, then volume will be a cube, and that will be equal to 4 by 3 pi r cube. So you must write a in terms of r. From there r will be under root 4, 4 by 3 pi 1 by 3 into r. From there also you can see that this r will be, for a spherical particle, this r will be under root 4 pi by 3. So this will be greater than r. So in this equation, you can write r by 2. So obviously this Vs will be larger than Vs. I hope you are getting what I am saying. Just just uh, forget what I have said. Just somebody said that I have given you non spherical particle. So what you that has equal volume, and it has length of a. It is in cuboidal shape, but volume is similar to this. The volume of this one is 4 pi 4 by 3 pi r cube, and the volume of your cube will be a cube. So from there your a will be this thing, and if you derive here, so you will be substituting r this d in terms of that length of a, and that a, what is a will be your this thing, 4 by 3 pi 1 by power 1 by 3 into r. So from there you can just check that you will come to know that this Vs is greater than uh, greater than this Vs for a non-spherical particle is greater than a spherical particle. I hope this is very clear to you. I have given too much time on this settling zone because this is very people make mistake in this question. And if you are appearing for gate examination every year, yeah, alternate year, you can expect a question from this settling zone. When I was appearing in 2021, I was asked. There was question related to the unit of viscosity. What is the unit? What will be the unit of kinematic or dynamic viscosity? There were four options, and it was 1 mark question. Similarly, question related to efficiency was also there. A question last year I did not appear, but in 2021 I have appeared. That time they were asking. Hmm. So as discussed, non-spherical particle will generally settles lower than a spherical particle. Hence, the correct option is A. Till now, I have covered total. There are total 10 questions, and till now I have covered all 9 questions. I am going to the last question. Till now, if you have any kind of doubt, any question, you can please ask, or I will move to the next question. Hmm. So this is a interesting question. In a monod equation, mu represents that substrate concentration at which a specific growth rate is half of maximum. So before answering this question, you should know what is monod equation, where it is used. Then only you can answer this, whether this option is correct or not. So this monod equation is used to describe the specific growth rate of microorganism as a function of substrate concentration. See, what happened that in wastewater treatment, there is tertiary treatment. Just let me check. I don't want to give any wrong. I don't want to say anything wrong. Let me clear. Uh, so our secondary treatment unit or biological treatment unit consists of bacteria. Secondary treatment is related to biological treatment. Means we till now till sedimentation tank. What we will try to remove all the inorganic component. If you have gone through the treatment plant, you must have observed that till sedimentation tank we have only focus on inorganic pollutant or inorganic particles that are there in the but as discussed in domestic wastewater, that majority of the portion is suspended in domestic wastewater is my organic component. So you have to degrade that organic component. So degradation of for degrading that organic component, we use some kind of microorganism. So that microorganism will eat it will eat that organic particles that is there, and that organic particle will act as a food for that microorganism. That is also known as substrate concentration. So this microorganism, its life means its how it is growing, how it is dying, the number of population of microorganism all depend on the substrate concentration. So how this microorganism is going, how the population of microorganism is increasing, these all depend upon uh, just one second. These all depend upon this substrate concentration. So there is term used food by mass ratio, that how much for how much food is present. Food is what is this, that organic component, and how much mass means how much organism. So what will happen that with time, currently I don't have, please just remember. So what happened that this microorganism, you know that this microorganism multiply in exponential ratio. So what will happen that this you will introduce some microorganism to your organic component, so it will start consuming that organic component, and it will start degrading all the organic component till all the organic component has been destroyed or not. So the growth miss, what we are trying to miss, we are providing some food to that microorganism, and that microorganism will grow. So how that growth happen in system, that is governed by monod equation. Okay, for this book I will refer you one book. When from where I have collected this data, I have collected one data, biological treatment unit by some foreign author. I will just at the end of lecture I will share that book. So the monod equation describes the specific growth rate of microorganism as a function of a substrate concentration. It is commonly used in microbiology and environmental engineering to model microbial growth in response to nutrition availability. So, what that organic matter is doing to that microorganism, it is providing some kind of nutrition to that microorganism for their growth. And the equation is given by mu m into S divided by Ks plus S, where different terms mu represents the specific growth rate at which rate this microorganism is growing, and the mu m is known as maximum specific growth rate. But at what maximum it can it can the growth can happen. The S is substrate concentration, that is food we are providing to them, and the Ks is known as monod concentration, representing substrate concentration at which the specific rate is half of the maximum. So this last statement will be explained to you by this graph. So I have taken help of this book, biological wastewater treatment theory and application by Grade and CP Leslie. So here you can see that this is growth rate of this microorganism and this is the substrate concentration. Okay. So what will happen that this growth rate will keep increasing depending upon the substrate concentration, and this is governed by this equation. Okay now. So so what happened that this growth rate is some ds by dt. You can mu, it is written as mu, but you can say that it is dc by dt. Means growth rate, if we are talking about growth rate, there will be some increase now. So it is dc by dt, that is increasing with substrate concentration, and this is mu m maximum. Sorry, this is ks is monod constant. When what will happen, this specific growth rate will attain some maximum growth rate. The half of that mu m at that miss at whatever point this substrate concentration is half of that mu m, that will be known as monod constant, and that is represent that's what is that is what it is written here. The monod constant representing the substrate concentration at which the specific growth rate is half of the maximum. Half maximum ka means half of the maximum. This is maximum and half of this maximum is here, and corresponding to that concentration is known as monod constant. Okay. The hence the statement is false. Why it is false? It is saying that mu represent the substrate concentration. Mu doesn't represent substrate. No. S represents substrate concentration and mu represent a specific growth rate. At what rate that microorganism is growing up. Okay. Similar to this, similar to this monod constant, there is one another equation that is known as Michel's-Menten kinetics. The equation which is given for this kinetics is also ds by dt, but here we are talking about enzymes, substrate and enzymes. So if you are into microbiology, you must have studied this thing about this kinetics. And here see this equation and this equation is same. Here they used instead of dc by dt, they used the term mu, but in this kinetics they just write the subtract miss ds by dt. Yeah, that is this q, and this is ds by dt is given by q. Okay. This q is equal to minus q max into s divided by ks plus s. So if you are really interested to know more about this thing, you can download this book from internet. So there is one more interesting thing. So we know that whenever there is a growth rate, whenever there is a when we are talking about this kinetics, so it will we should always talk about the order of reaction. Suppose we said that concentration of anything is increasing or decreasing, then whenever we are discussing that, we should always discuss at what rate or in what order that is. Whether it is zero order, whether it is first order, whether it is second order, we should know about this thing. So the interesting part of this monod equation is that up to this half of maximum specific growth rate, the growth is following first order reaction, and after the half of from half concentration, half a specific rate to maximum concentration rate, it is following zero order reactions. See, this is the representation is different in different way. That's why you might not be familiar, but when people have plotted the growth rate with time, yeah, concentration with time, they have seen that up to this point the order is first order reaction, and after that the order is of zero order reaction. So generally a question is asked in many competitive exam, that what is the order of reaction. Okay. So I was saying that from about this book, you can just uh, download this book from uh, see, free PDFs are available. You can read this book. They have described it in a very in a very detailed way. You can download it from here. I am just sharing you the. I'm just sharing you the link. You can download it from here. Or what you can do, that you can, if you have your miss, you can find this book in your library also. So you can. But if you have, you can, if that this book is present in your library, you can study from there also. Okay. So till now, any doubt? So there is no further question. So this was the last question, and the answer of this question was this statement was false. So we have more 5 minutes, and 5 minutes is just for a common discussion. If you have any kind of doubt, you can ask me. Usha, Raju, and the only two people have joined. So I will request you, if you have 5 more minutes are left. If you want to ask anything, you can ask. I will just ask. I will try to explain in a very short way. I hope you is whatever what I was trying to explain to you. You were getting it, and these were some basic questions that is being discussed everywhere. Yes, I was just giving a overview of treatment plan. Do join next week also. From next week, some advanced treatment method will be there. We will talk in more detail how this, after all the inorganic particle has been removed from the system, how organic particle will be removed, what is different kind of, uh, how this microorganism works, and all this thing. So, so you can turn on your mic and you can ask, or I if I do not get reply, I might in the meeting. Sorry. If you have any question, you can ask, or we can end the meeting. Hello. You can type also if you are not.
Thank you so much. You can end the meeting, please.